International Space Science ISSI, located in Switzerland. If you're not familiar with us, there is a leaflet, saying what we're doing and what we're there for. But we're an international institute in Switzerland, and that is why we're proud today to serve the Swiss community as the Swiss node of an international network broadcasting the release of the first images and spectra of the James Webb telescope. As a Swiss node, we're focusing on Swiss scientists and Swiss contributions to the hardware, and that is why we invited, prior to joining the broadcast from NASA, ISSI, and the CSA, Swiss scientists, to tell us about what they do and what their hardware contributions is. At this point, I wanted to thank Antonella Natta for actually pointing us towards that opportunity. We had missed it had you not, told us about it. And thank you very much. And this was really good. Swiss telescope, space telescope is not here yet, really. Anyways, okay, so he was to be here. But I'm content to single out just one person to welcome specifically, and this is Claude Nicollier, the Swiss astronaut who helped prepare the predecessor of the James Webb telescope, the Hubble telescope, back in the 90s. So thank you very much for joining us, and thank you very much for being here with us today. As you know, space science, space research is very expensive. And it needs to be funded by public money. And in Switzerland, this is the SSO, the Swiss Space Office, where the money comes from. And I'm very delighted to have Valerie Koller here with us to say a few words of welcome on behalf of the SSO. Valerie, please.
Ladies and gentlemen, dear professors, colleagues, and friends of our universe. Mr. Fon, thank you very much for the warm welcome. It's a great pleasure to be here. And today, the invitation of this very first data release of the James Webb Space Telescope. Thank you for the organization of this event and for the kind invitation to say a few words at the beginning of this event. This telescope will, without any doubt, launch the beginning of a new era of astrophysical research. And we at the Swiss Space Office of the State Secretary for Education, Research and Innovation are happy and proud to be able to support this great contribution to this masterpiece of engineering and roadway science. The Swiss contribution was enabled through Switzerland's membership. And Switzerland's founding member. Through this membership, Swiss actors have the option of the possibility to participate in development, procurement. They have access to scientific data, and they can collaborate in these international endeavors, as is the James Webb Space Telescope. And by the way, the telescope is a short name, simply Webb, and it's an abbreviation. I'm sure that the people of Bern who have an affinity for nicknames will much appreciate it. So I'll just refer to it as the Webb to save some time as well. Switzerland had its share of responsibility at the launch of this telescope. It was launched on an Ariane 5 with the support of space. They now renamed to Beyond Gravity. And thanks to this launch, Webb required to deliver the science that you're about to see. And since the year 2004, Switzerland supported the instrument contribution, to the infrared instrument, the project program of the European Space Agency. This program we use to finance all the scientific instrument contributions to the different missions of ISA and of other agencies as well. The Swiss contribution was originally led by Dr. Alexander Sinde from the Paul Scherrer Institute. And I learned that a few colleagues from the Paul Scherrer Institute are here among us today, so welcome to you. And in 2008, the project moved then to ETH Zurich. And there, Dr. Adrian Glauser is also here. From the Project of Physics and Astrophysics, have led the Swiss project ever since. We've also coordinated the contributions by the different industries to the MIDI instruments. One of them was provided by the Beyond Gravity, and so former RUAG space. It's the contamination control cover to protect MIRI from doing its cool down phase of testing and also following the mechanism. Is also it acts as an optical shutter, allowing for onboard calibration and detection of the sensors. There was another contribution by Webb. They developed the special cables, bio cables, which are made of 250 electrical wires. They connect the cryogenic sensors of the cold, very cold optical bench, but we'll hear about the temperatures I think afterwards, to the warm electronics. The MIRI instrument is an ISSI-NASA collaboration, and it's one of the core Webb instruments. It's the only one that covers the range from 5 to 28 micrometers, and it has the capabilities required to cover basically all of Webb's research activities, which is, again, we'll certainly hear about that more at a later point. I'm sure that all of you have seen the first image, the Webb deep field release yesterday, and I guess all of us have a personal reaction to it. And for me, it's actually, it made me remember the time when I first learned about gravitational lensing, which was actually just a few hundred meters from here at the University of Bern. And that was how it was described to us that it should look like, basically. And now we're looking at this image in the sharpest infrared image of the distance universe today. So that's quite exciting. I'm thinking that Webb will inspire many more generations of astrophysicists, of engineers, and basically curious minds in general. There will be future missions. We at the Space Office can't wait to see the science coming out from the Webb, and I would like to congratulate all those people involved for outstanding achievements. And I wish you much joy and
Adrian Glauser, the Swiss National Project Manager for the MIRI, the mid-infrared instrument. The Swiss hardware contributes, I understand, to the mission, and a researcher in the field of exoplanets from the ETH in Zurich. Adrian was so kind to provide us with this model of the James WST. It was shipped over with a big truck, much too big from Zurich, and here it is. We're very proud to have it here. And he also brought a model of his instrument. And the talk will be on James WST and his contribution to MIRI.
I thank you also, Valerie. I think you took away most of my time pressure that I have because we produced so well MIRI and our contribution. So, ladies and gentlemen, welcome. Thank you very much for having me here, in particular for organizing this event here. I'm grateful we can celebrate this together as a Swiss community here in Bern. The first release of pictures and spectra of the James Webb Space Telescope. I'm going to briefly introduce James Webb before I then focus on the Swiss contribution and the path that led from ancient past at Paul Scherrer Institute to ETH now and the science we do now all together among Swiss institutes. So the James Webb, without further words, has its most distinct feature, which is this large 6.5 meter diameter golden shining mirror. It's made of 18 beryllium segments, and it has been deployed because it was in a Ariane rocket in the US. And with that large diameter, together with its infrared sensitivity, it really probes a part of the universe that we haven't been able to probe before. It is often called the Hubble successor. I just had a conversation with Claude Nicollier before what that actually means in terms of sharpness and resolution. I think it's not fair to say that in most parameters except of the science that will be continued with the James Webb. James Webb is complementary to Hubble. That's the way I would like to see it, because we had infrared missions before. The Spitzer mission that really already had a very good probe of the infrared universe. However, if you look at the mirror size compared with Hubble and compared now with James Webb, Spitzer was tiny, and yet it provided us access to this great window. Now James Webb brings the combination of the sharpness of Hubble together with the wavelength sensitivity of Spitzer And with its large collective area, we have a very, very sensitive instrument. In order to achieve the sensitivity, and because we are doing infrared, we need to cool down the telescope, the entire telescope, including its instruments, down to temperatures of -230 degrees Celsius, or people who like to count from the absolute 0 point, if we go to 43 Kelvin, more or less. Not all the mirrors are the same temperature, but that's roughly. One of the instruments has to go even further down. It operates at 7 Kelvin above the absolute 0 point, or -266 degrees. In order to achieve this temperature, one has to passively cool the telescope. That means one has to block the solar light in order to just have the dark and cold cosmos that can be used for radiative cooling. And to achieve that, there was this huge sun shield built, has the size of a tennis court, made out of 5-layer of multi-layer insulation, as you can also see in the model here, that helps to block the sunlight. However, this is not sufficient to make such a thermal instrument. You need to go to an orbit that is not around the Earth, because otherwise you would see the Earth every half orbit, and then you get the heat back from Earth. So one has to go far away, and the Lagrange point 2 point, which is roughly 1.5 million kilometers away from Earth, that is a distinct orbit one chooses for cryogenic missions like the James Webb mission. Now, it is not a single point. The L2 is a mathematical point, but the orbit is rather more a halo around the point, and this goes rather slowly. Right, so James Webb is built for many science topics, but it has been promoted as servicing those 4 science themes in particular. So it starts with the first light and realization. It studies the assembly of galaxies, birth and stars of protoplanetary systems, and planets and the origin of life. Now, you can also illustrate this in a diagram that shows the history of the universe. So if you look basically back here to the Big Bang, and there was an epoch after the cosmic microwave background that we can observe roughly 4,000 years after the Big Bang. It was a long period of not much happening because the universe was opaque and there was nothing shining. And then at some point, clusters became more dense, galaxies were starting forming, and the first light started to be emitted in the universe, then finally leading to a transparent universe that you can observe. But with James Webb, the goal is to probe all the way back to this very, very early epoch of galaxies being formed. And if you can achieve that, then basically you see all the way up to present day. And the local universe, and of course you see star and planet formation regions, and you can study exoplanets. Now, I'm not going to talk about those 3 topics because we have distinct speakers after me, but I focus just a little bit about the exoplanets because we're going to see today also something in that regard. And I'm going to briefly introduce you so that you're prepared for understanding what it will be later. So exoplanets, we know today that we have more than 5,700 discovered. There are many more to come. And what we know already today is they are diverse. They are not like the solar system. They are many sorts. What we really would like to do is to characterize what they are made of, what is the composition, what kind of gases do they have in their atmosphere. In order to do that, we use with the James Webb Telescope 2 techniques. And one is the transit spectroscopy. That's one of the techniques you are going to see today. And so what happens here is that the light, the planet is oriented such in an ideal way that it actually makes an eclipse when it orbits around the star, such that we see a little drop in intensity during this eclipse. And because we choose here WASP 90-something, I forgot the number, this is a huge gas giant with a large atmosphere. It actually allows us to probe the atmosphere while light is going through, and we just observe this fingerprint, this molecular fingerprint that is then being left in the atmosphere in our spectra that we observe as James Webb. So this is the so-called transit spectroscopy method. So there is another method with James Webb that we can use. This is called direct spectroscopy. We're not going to see data of that today, but we will take data. If with this large mirror we can spatially separate the exoplanet from its host star, we can actually make spectra simultaneously into images. And then next to this bright starlight, we can extract the spectra of the exoplanets. I will come back to those two plots in a minute. So in order, then you can probe water features, for example. You will see real data from James Webb later. This is from now. So in order to do the science, you need science instruments. So always forgotten that a telescope is great, but the only function a telescope has is to collect light and to re-image it in a focal plane. And if it does it well, and James Webb does it perfectly, then the job of the telescope is done. What really then starts is that the light needs to be analyzed according to your measurement you want to do. And for that reason, James Webb has 4 different instruments. 3 work in the so-called near-infrared, those who like wavelength numbers from 0.6 to 5 micrometer. So they are operating at the temperature of the telescope. So this is a near-infrared camera, a near-infrared spectrometer, and this is a near-infrared slitless spectrometer from Canada. The only instrument that operates in the mid-infrared, so that's further away from the visible range, is MIRI. And also there are NASA ISSI flags, and there is a good reason for that. MIRI is actually built by a European consortium of partner institutes, of research institutes that proposed that James Webb must have a mid-infrared capability. It was not foreseen at the beginning of that. So MIRI was therefore not funded through space agencies, but it was funded through national agencies. In the case of Switzerland, as mentioned before, it is the products program of the Swiss Space Office that actually actively contribute to develop and pay hardware. So MIRI has 2 main subsystems. Unfortunately, animation is a little bit bumpy, but bear with me. The first one is the one you're going to see images from later today. That's the imager. And what we see here is the beam coming in from the telescope, going into this imager and being then re-imaged to the detector. So we see turning right now is a filter wheel. And with that filter wheel, we can actually select different color filters to make false color composition images. What you see here is still an animation. I have to replace this now, actually. And this is, of course, monochromatic. So this is an exposure of a single filter, but with multiple filters. And you are going to see several nice images today with multiple filters. You will see that they are made from this filter wheel. In addition, we have here on this filter wheel also a prism. And with that, we can also use slits in the imaging mask to do slit spectroscopy. So we have here a spectroscopy mode, and we have also a slitless spectroscopy mode for the exoplanet transit spectroscopy, as I introduced before. And the last one, unfortunately, we're not going to see yet, but we will see data soon, is the coronagraph of MIRI. That's something we use for the direct spectroscopy I was mentioning before, where we can actually block bright stellar light to see faint companions around. The other subsystem is on the other side of the deck of MIRI. And we see here again the animation. The light comes from the telescope, but now it's being relayed into the lower part of the instrument. And you see here now how it is split up spectrally into 4 different bands. And it's now going into this mirror that I'm going to talk about a bit later. And it's being flipped soon to the other side again, where the main spectrometer optics is, where we have a grating that disperses the light. And I think this animation just shows you beautifully the complexity of such an instrument. It is a spectrometer, but it's much more than that. And it has all to be built in a very compact volume because you do a space instrument, so you may compromise the factor, but it's a beautiful instrument. So this mirror there, what it does is basically it takes an image and it slices it such that we can reorient or re-image those slices in a horizontal way so that we can disperse all the slices together. And with that, that's how it looks on the detector. We can reconstruct both the image and the spectrum, and that's ideal for doing this direct spectroscopy as I was introducing before. One of the use cases. All right, so all that is MIRI, and Switzerland has this important role with it. As mentioned before, everything started at the Alger Institute back in 2003 with the group of Dr. Alex Zander, and I'm very glad to see former colleagues from that time sitting in this room. Wime is also here. He was at the Rural Space at that time. It was called HTS. I don't know how many rebranding this company went through, but so we developed together these mechanisms and the cables. I'm going to talk about that a little bit more. Back in those times, then in 2006, the construction and testing started. In 2008, so 14 years ago, we delivered the hardware already. Now, these are components. This is not a subsystem or a system, so it took some more time until the system came together, this MIRI system. And that happened then in 2011 when we did the tests. And then it was basically integrated to the observatory level and tested again, and happened during that time. And as mentioned before, we moved the project from PSI to ETH at the moment of the hardware production. Now, one aspect, and you can see later if you want, a little flight spare cable here. Cables don't sound very complicated, but they are actually, if you want to build cryogenic cables that have a minimal heat load into the instrument. Because MIRI is the only instrument that works at 7 Kelvin, so much lower temperatures. All electrical connectors need to connect to a warmer environment, and any electrical connection is also a thermal bridge. That means you need to minimize the thermal heat load going through these cables, and that only can work if you use very exotic materials that are very difficult to solder, and everything has to be spacer-proof and cryogenically compatible. So that's not a process you invent overnight. And this took us several tests. You see here in front of the PSI test chamber, where we underwent several test campaigns with flight hardware, how we measured all the the other contribution was mentioned before already, is the contamination control cover. It looks like a simple mechanism, but actually it's not, because the purpose of this is during the cool down, because MIRI is the coldest instrument, we want to prevent ices that are circulating in the environment from the structure being sticking on our cold mirrors. And in order to prevent that, we wanted to shut and close the instrument, cooling down, and then to open it. And what is the complex part of it? It has to open. It has to open. And in order to achieve that, we need to test and test and test and retest and retest. And we had many stories where we went under things that look simple, but they are not. And so I hope you can appreciate a little bit by looking at the flight spare model over there, that this is actually a real development that took us years. Right, so with that, we delivered, as mentioned, everything into MIRI, and then it was cryogenically tested in 2011, where we had a test campaign of more than 3 months non-stop operation. And it was a very exciting time because we really was making this instrument real, and so once that was completed, where we delivered MIRI before we shipped it and integrated it to the integrated science instrument module. Here you see already its counterpart. Here it is. Then all the instruments together, they were then again 3 times cryogenically tested at the Goddard Space Flight Center over the period of more than 3 years. This is a huge vacuum chamber. I don't know whether you can see it, but there are some people standing around. So this is a very large facility where we again did several months of test campaigning, calibrating the instruments and seeing it until the marriage with the optical telescope, and everything was then moved to Houston, to the Johnson Space Center, to the huge vacuum chamber there, where we also did a full end-to-end optical test. And this was a remarkable event. Then, yeah, the marriage with the solar shields. I think from here, maybe you will see the features. But then, once this was done, we tested, there were some issues during that period that caused further delays. But then things were wrapped up, packed, and shipped to Vienna, where on Christmas Day last year, we had finally the launch. And although we have seen it maybe multiple times, at least I have seen it so many times, I cannot resist to show it to you once more, because I think it really marks a highlight of that project where things go from ground up and things have to work autonomously, or at least remote controlled. The launch was actually so perfect, and that was one of the parameters that was a bit unknown, how well will be the launch, because from here onwards, now we see James Webb being undocked. James Webb has some fuel to bring itself to the L2 orbit, but depending on the launch trajectory, the fuel consumption during that fluid transfer was more or less. And the launch was so perfect that we saved so much fuel that the lifetime of James Webb is not anymore 10 years, but most likely 20 years. So we just extended the mission by a perfect launch by a factor of 2, or you could say the price per hour observation has decreased by a factor of 2. So I think that's remarkable. Right. Since then, those scary moments or days actually happened where everyone that was involved, not involved, really was worried about this very complex deployment that was required in order to ship such a large spacecraft into space in an Ariane rocket with a much smaller volume. However, without any glitch, this worked just perfect as you would design it on a paper, and there was no single issue that would have caused any issue. So the performance of the telescope, the thermal performance, which was critical because if the deployment of this large mirror sun shield would not have happened as planned, then of course the thermal performance will not be the same. But what we see from the thermal data, this telescope is just operating perfectly. Right, so what happened since? First of all, the 18 segment had to be aligned. And we saw the first aligned images of Webb in mid of March. And since then, we were doing commissioning, as we call that process, of the science instruments. Here is the Swiss team in Baltimore at the Mission Operations Center during a night shift. And yeah, we supported calibration activities and also the real hands-on work that we have to do on console. And my colleague, Kronis, is still over there and still continues doing some commissioning activities. And yeah, here you see now basically a sharp image of all the instruments as they are in the field. And Miri over there, just highlighting the comparison with its predecessor, Spitzer. It's a more or less same wavelength. And WISE, which is inframission, you just see the improvement in terms of sharpness. And there is so much more you will see today. Right, with that, the instruments are ready for science. Miri had its successful review 2 weeks ago, so we are complete with commissioning. There are some tweaks in terms of calibration, but that doesn't mean we are not ready for science. So we are ready, and you will see the results today. And with that, it is time to hand over the keys.
The next contribution will be a shared contribution by Pascal Oesch and Anne Hammer from dark to light, the first generation of galaxies.
In the same epoch in the history of the universe, which is the very first billion years of galaxy evolution, but with complementary approaches. So I'm doing my postulations, and Pascal is an expert of observations of very distant galaxies. But we aim to answer the very same questions.
There is maybe a switch on.
Oh, yes.
Sorry.
Okay. And how did the first galaxies form? And what physics governed their build-up? So this is a timeline very similar to the one I showed earlier, of what astronomers really understand on galaxy formation and evolution, with an emphasis on this early cosmic history. So starting from around 400,000 years of Big Bang, which is the limit of the observable universe, and this is also the time where atoms form for the first time in the universe. So the matter at this time form atomic gas, mainly composed of hydrogen. So unusual. Gravity, the first structures for stars and first galaxies. And once again, the big question here is how rapidly these first sources of light appeared in the universe. But what we know, however, is that only after 1 billion years of evolution, these very first sources of light seem to be efficient enough, seem to produce enough energetic radiation so that the universe got reionized or heated as a whole. And since then, the universe, so it is now completely ionized. And since then, the galaxies are evolving in an ionized universe. So our scientific motivations are to understand this major phase transition in the history of the universe, where things from neutron to ionized in one behavior, and that we are calling cosmic reionization, which is not easy to say. This early cosmic history is also the ideal laboratory to test our models of galaxy formation. How fast can we form a galaxy? And build our cosmology. So, in order to answer these questions, we will put simulations of galaxy formation. So, I will show you a film of a representative volume of the universe, where matter evolves. So, the distribution of matter in the universe evolved through gravity and hydrodynamics, and the galaxies evolve. So the matter evolves as a cosmic web, and galaxies grow at the nose, starting with smaller galaxies. And in these simulations, we also model the ionizing emissions from each stellar particle in the galaxies, and we follow their transfer through the interstellar medium of the galaxies out in the intergalactic medium. And so, from state-of-the-art simulations from the simulations is yes, stars in primordial galaxies to reionize the universe. So, one very first step to assess the realism of these galaxies is to produce mock observations of our virtual galaxies, and this is actually my specialty, to compare with observations. And so this is an illustration of the diversity of galaxies that we have in our simulation volume, from very small galaxies to much bigger ones. And these are examples of mock observations of these galaxies. This is a UV image taking into account dust attenuation. This is the spatial and the spectral distribution of the very strongest line of hydrogen, which is called Lyman alpha emission. But as you can guess, these mock observations are very idealized with a very high spatial and spectral resolution and also a very low noise. But we can also do more realistic mock observations of our galaxies. And this is, as an illustration, what James Webb would see for a very big galaxy in our. So I was asked, why do you need simulations? Since very soon with James Webb, you'll get real images and real spectra from real distant galaxies. So this is my attempt to convince that actually you need both. Simulations and observations are two complementary approaches that we need to pursue in order to understand the reality. So you have to keep in mind that we can observe only the brightest galaxies because they are so much easier to detect. Whereas in simulations, we don't have any prior, so we are modeling the whole galaxy population. And so in order to compare the distribution of luminosities in our simulations and observations, we do what we call luminosity functions. So this is just accounting in our simulation box how many galaxies of different luminosities we have per unit volume. And we see that at the brightest end for the simulations, these are bright galaxies, which are big ones. At the bright end, we match the number counts of galaxies detected by observation. So this gives you confidence that these simulations can be used to study the whole population of galaxies. And for example, to test or quantify observational biases, like how many galaxies are observers detecting compared to the whole distribution of galaxies. And also, we can look at, try to understand what are the physical mechanisms which govern, why is a galaxy bright or faint in Lyman alpha? What are the physical mechanisms for that, which would help the interpretation of observational data. And in the last minute, I just want to flash what I'm very looking forward with James Webb. So I would like to, so as I told you, simulations seem to indicate that galaxies can realize the universe on time. But it would be much more comfortable if we could check on observed galaxies and probe that they are emitting some ionizing photons. However, it's impossible. So this is a schematic view of a very distant galaxy, which is leaking ionizing radiation in some directions. And the easiest would be to observe this ionizing radiation directly, as you can do in the simulations. This was the yellow flashes in the film that I showed. But actually, this is we really expect that James Webb will detect no flux here in this ionizing part, because this radiation is actually absorbed on the way to reionize the universe. So with the simulations, we calibrated in direct traces. So we were looking for spectral features that are predicted to be very different when you're looking at a line of sight where there is ionizing radiation leaking, and a line of sight which is opaque to ionizing radiation. And this, for example, this magnesium doublet will be soon observable with James Webb from very distant galaxies for the first time. So I'm very looking forward to see this kind of spectrum. And I let the floor to Pascal. That's why James Webb is so efficient in high-redshift galaxies.
Well, merci beaucoup. Thank you very much for the invitation. Yes, indeed, I specialize in observations of very distant galaxies. And so before we use Webb to push further back in our cosmic history, I just want to start with this quote by Ed Hubble, which is the history of astronomy is a history of receding horizons. And as you see in this animation here, in this illustration, this is exactly what the Hubble Space Telescope was doing for us over the last 30 years that it was in space, thanks to astronauts who were fixing it indeed. So when Hubble was launched in 1990, what we knew about star-forming galaxies about halfway back across cosmic history. And so here we can see redshift indicated here. So we're really talking about this redshift. That's what we measure the distances to galaxies. The higher the redshift, the further back in time we're looking. Here at the bottom, we see the time axis. And so since about 2009, when the last servicing mission of Hubble was performed, the V3 IR camera was installed, we finally were able really to push into this first 1 million year of cosmic history that Anne was talking about, where the universe transitioned from dark to light. But we have not seen the first galaxies yet. And I will show you why. So first, how can we identify these early galaxies? Well, we're actually making use of the neutral hydrogen in the intergalactic medium. And so when we observe a distant galaxy, you can see very well here, but it's just blue young stars in the source, it's a star-forming source typically. And when these photons of this galaxy travel towards the universe, towards our Hubble Space Telescope or any observer, they may encounter a neutral hydrogen atom. When they encounter this atom, either they can excite this electron, or if they have enough energy, these photons, they can completely ionize this atom, so separate electron and proton. But that means that these photons are now missing from our observations. And as the photons continue to travel from this galaxy, it doesn't appear blue, but it appears red. So, and also because the universe is further expanding. And really, this is the technique that we're using with the Hubble Space Telescope, and that we'll be using with James Webb in the future to identify these very distant sources. And here you can see an animation of how we do this actually with Hubble. So again, we're not using these beautiful color images. We have individual images at different wavelength ranges. So on the top here, you see the different filters we currently have available with the Hubble Space Telescope. We see how this galaxy would look like in the two different cameras on Hubble. And here's a spectrum of the source. And as we go now to higher and higher redshifts, so earlier and earlier cosmic times, you can see how this absorption here at the Lyman alpha line gets stronger and stronger because the universe becomes more and more neutral. And so this particular source here, at 7, once we're in the first 1 billion year of cosmic history, you can see that these galaxies are completely invisible in the optical, in the original Hubble Ultra Deep Field. And that's why we needed the V3 IR camera to really push into this realization effort. But the problem now, as you can see, what's happening here is now by redshift 10 and 12, this galaxies shift out of the wavelength observational window of the Hubble Space Telescope. So we've reached the absolute limit at the moment with Hubble. And at these particular redshifts, we only know a few galaxies, a handful. But there's one in particular that was mentioned earlier. This is the most distant source we've ever found. That's GNZ 11. This is this galaxy, so people don't necessarily know that, yeah, Switzerland was holding the record for the last 6 years. And yeah, hopefully that will be overcome very quickly. But anyway, so this is the source here. It's relatively bright for the time here. It's only 400 million years after the Big Bang. If you see the images of this galaxy, you can see that it's only detected in one filter, as you saw in the animation before, and it's completely invisible at shorter wavelengths. Yeah, so in that sense, of course, we really don't have a lot of information on this galaxy, but we only have this one image. It's actually detected also with the Spitzer Space Telescope that gives us information about the stellar mass of this source. But really, we need much more, right? And so that's just showing you here kind of an illustration of the spectrum, the spectral energy distribution of a galaxy in the early universe, where it sits, not slightly later, cosmic times. Here you see the wavelength. Then in blue, that's the stellar and nebular emissions, so the emission of gas in the stars. And then maybe if there's some dust in this galaxy, it might absorb some of this blue UV light, and it will be re-emitted here at the millimeter wavelength. And so now if you observe this galaxy, as we said, with Hubble, we really only have a very narrow wavelength window that we can observe these sources here in the red-stream ultraviolet. And so that only gives us information about the star formation, the recent star formation in these sources, if there's no dust. But really to get a comprehensive view of these early sources, we need to combine our Hubble observations with other facilities, including ALMA, but in particular what I want to focus on here is Spitzer. So Spitzer has been really this tiny telescope, as we've heard, but really has been quite successful in providing some clues on this wavelength window here at 4 to 5 micron. And that's really critical if we want to understand stellar masses of these sources. We need to measure the older stellar population in this galaxy. When did they start to form those stars? Now, of course, with James Webb, I mean, this is really going to be a complete revolution, right? We will have access to this full wavelength window. You see all these emission lines here. Every single of these lines is full of information on the physical properties of the sources. We get a huge gain of information. And we've seen this before. I mean, in a sense, the James Webb is not just a successor of the Hubble Space Telescope. I completely agree with Adrian here. I mean, Hubble and Spitzer together are, well, James Webb is 100 times more powerful than Hubble and Spitzer together. And in particular, on these wavelength ranges in the infrared, that's where James Webb really will shine. Before we just had the Spitzer Space Telescope. And it's not just again resolution that we will get, but it's really the gain in wavelength information, the infrared, that will really completely transform our view of the early universe. And just to illustrate this, given the image that we saw yesterday or this morning, very early. So here, this is an image of the same cluster with the Spitzer taken over the last few years. This is infrared now. I'm showing the Hubble image, and now here, this is the new James Webb image. And just flicking back and forth, I mean, there's a few galaxies that you can see here. This one, for instance, where quite literally James Webb is just, making the invisible visible now with these new wavelength window. And so there's many of these galaxies, and we're really looking forward to analyze the data. Okay. So then the other thing, it's not just imaging that is really revolutionary, but it's also the spectroscopy. To split the light into its components with prism. Currently, this is just showing some emission lines that we can probe with ground-based facilities. Emission lines, but that we're using routinely to probe the physical properties of galaxies. And at the moment, we can only probe these out to redshift 2 to 3, so that's kind of the peak of cosmic star formation. But then with James Webb, with NIRSpec, we will be able to probe all of these out to the highest redshift, so into the first generations of galaxies. And again, that's going to be completely revolutionary. It turns out that 70% of the first year cycle will be done in spectroscopy. Unprecedented. And for the very distant galaxies, for instance, these are some simulations of what we expect that we will be able to see for some of these early sources. Again, we will be measuring all these emission lines. Again, no technical details, but these give us information about the physical properties, dynamical state, the ionization state of the gas. And in particular, they will tell us how quickly these galaxies build up the heavy elements. I mean, again, we've heard in the early universe, we only had hydrogen and helium, but they're all made of carbon, oxygen, more heavy elements. And exactly in these early galaxies, that's when they started, when these first elements were starting to be formed. Okay, so So then let's go to the kind of programs that we're doing here in Switzerland. First of all, I want to point out that I'm very proud. Switzerland has been, apart from having access to guaranteed time observations, thanks to the MIRI team, we also were very successful in getting proposals accepted, 8 proposals that are being led by Swiss community on different science topics. And I just want to highlight what we're doing in Geneva in particular. So one, I'm leading 2 programs. One is an imaging program. It's called Panoramic. So here we're going to be taking lots of different images, kind of distributed around the sky. Again, in these new filters, completely revolutionary and unprecedented view of the universe, and that will allow us to click the probe to the very highest, to the earliest sources. And the second program that I'm leading is a Griffin program. So we're taking spectroscopy with the near-time camera. It's called Fresco. Here again, no need for the technical details, but we will be able to measure the distances to sources very accurately, thanks to these emission lines, to figure out how much they contribute to ionization. And George Matteo over there actually is leading another small program also with exactly the same. Then in Geneva, we also have Daniel Scherer, our colleague there, who is leading a medium program, Lyman Continuum 22, which is really probing these features that Anne was showing you earlier. And here's again just an illustration of the expected spectra that we expect to see from NIRSpec. Then Mirko also in Geneva is leading a program on figuring out what's driving star formation in giant molecular clouds at slightly lower redshift, so it's slightly later cosmic times. In particular, using the NIRSpec spectrograph in the IFU mode, getting spectra at every single pixel, combining this with the ALMA data. Then we have Laia Barufet, who is leading a program on, again, the dusty red sources, one of those sources that I was just pointing out earlier. We have known those sources from Spitzer, but we don't know their nature, and so we're finding a spectra for some of these. And finally, completely differently, Elizabeth Matthews, also in Geneva postdoc, she will be doing chronographic imaging from Jupiter analog. So lots of amazing data that will come and basic science that will be done over the next few years here at Swiss Space. And so I just want to finish again with this quote that the history of astronomy is a history of receding horizons. And with Hubble, we have come a very long way, I think further than we would have expected, again, up to redshift 11, really stepping on the toes of James Webb. But really a new chapter in the history of astronomy is about to be written. With James Webb now. Really don't know how far back James Webb will bring us, but it's really exciting to be among a generation of astronomers who can use this telescope and finally find.
Then let's move on. Our next speaker will be Beatrice Coulthard from the Center for Space and Habitability of the University of Bern.
Thank you very much for the introduction. So, I just it is my pleasure to be here today and to talk to you about how the building blocks of life are making into ISIS and ISIS for us. So just briefly to motivate this talk. So the building blocks of life that make up our own bodies as we know them are predominantly made out of 4 elements: hydrogen, oxygen, carbon, and nitrogen. And they are only available in the thin surface layer on the Earth. So we believe that they have been delivered to Earth in ISIS due to cometary impact at some point in time. And the major components of those ISIS might have been quite simple. So the predominant species in the ice will have been water, methane, ammonia, carbon dioxide, and carbon monoxide. But it is also very likely that those ISIS consist of, to a smaller degree, of more complex species. For instance, they can be made of often alcohols, methanol, and ethanol, or also simple sugar like aldehyde. And I'm an astrochemist, so when I speak of a complex organic molecule, I talk about everything that has at least 6 atoms, and one of them has to be carbon. So for an astrochemist, this is already quite complex. And one thing that I want to highlight in regards to Bern is the Rosetta mission that visited Comet 67P during Paris and followed the comet for more than a year. And an instrument that was led by a team in Bern by Katrin Altweg detected glycine, the simplest amino acid, for the first time in a comet.
So this strengthens the hypothesis that the simplest building blocks of life can indeed be delivered from comets to Earth, and also that they are already made in interstellar ices. But now the question becomes, do also other icy planets possess those ingredients of life? And for that, we need to look into the question of how do those interstellar ices actually form. And we know that ices actually form before stars. So what you can see here are the molecular clouds, which are surrounded by the interstellar matter and radiation surrounding those clouds. And in molecular clouds, at some point, star formation and planet formation will occur, but before that, already ices do form. And if we want to talk about ice formation in molecular clouds and also the possibility of them making comets in our solar system, we also need to talk a bit about star formation in general. So at a first step, there is a so-called pre-stellar core. Those are quiescent objects. So they have no protostar yet, so they are not heated by an internal luminosity source. And at some point, t equals 0 in time, they start to collapse and will eventually form a protostar. And in the first 10,000 to a few 100,000 years of the life of a protostar, an envelope consisting of dust and gas will feed material onto the star, so it becomes more luminous. And at some point in its evolutionary stage, a protoplanetary disk where planet formation occurs will also start to form. And after about 1 million years or so, the envelope has dissipated, but the protoplanetary disk is still there and feeds material onto the star. And then, at some point in time, we end up with a planetary system. And in the case of our solar system, we have a planetary system that has icy bodies outside of the system and rocky planets at the inside of the system. We can observe it at a time of 4.5 billion years. But planet formation occurs much earlier, already in the stage where the protostar is embedded, and then when the envelope is dissipated. So in order to find out what those interstellar ices are made of, we actually need to trace the ice evolution through all these different steps of star formation to find out what will end up in the solar system comet. And in that regard, one parameter that needs to be talked about a bit is temperature, because the temperature during the different stages of star formation goes quite up. These stellar cores are quiescent, and as there is no protostar, they are very cold. So the temperatures that are found in them are just 10 degrees above the absolute 0 point. But once a protostar has formed, ices that come in close proximity get destroyed. But the outer parts of such a protostellar system are cold enough so that ices can still be formed, or that they can actually survive during the different stages. This is also true once a protoplanetary disk is there. Close to the protostar, again, the ices will be destroyed, but in the middle of the protoplanetary disk, the temperatures are cold enough so that ices can reform. The question that improves about what ices are inherited is split into two parts. So first, we want to know which ices do actually enter the protoplanetary disk, and then we want to know which ices survive to make up the small bodies that start to form planets or comets in the end. And we also kind of want to find out which ices are inherited in which stage of star formation. And so far, we only had Alma to tell us a bit about around this. So Alma is the color-rich stability center. And with Alma, we are able to observe complex organic molecules in the gas around protostars, and to a lesser degree also around protoplanetary disks. But the complementary part, so the ice content, and if comps can actually observe in the ice, we don't know about them until today. And this is where JWST comes in. So with JWST, we will be able to observe complex organic molecules in the ice around protostars for the first time. One program that is designed to tackle that is the so-called ISSI program. The ISSI is led by Melissa McClure at Leiden University in the Netherlands, and the team consists of 49 members in 11 countries, and I'm proud to say that Switzerland is one of them. And the team consists of observers, laboratory astrophysicists, and also chemical modelers. And the really amazing thing about it being an ERS program is that the data will be observed in the next month. But as soon as the data is really accessible to the team, everyone in the scientific community can also look at the data. So only in a couple of months, everyone that wants to find out if we can actually observe comps in the ices around protostars can take a look at the ice age data. And this is also the only star formation proposal amongst the ERS programs. So how is ice age tackling the question of how or if unveiling books of life can be observed in ISS. So Ice Age focuses on observations in one molecular cloud, the chameleon region. This means that all ices there have the same formation history, but they are going to look at different sources within this cloud. So they are going to look at a pre-stellar core and a very young protostar, and also at a more evolved protostar and a protoplanetary disk. And in the first step, Ice Age will make use of JWST's new wide spectra to map 140 background stars to learn about the chemistry in the cloud. And it is amazing because this is about 10 times the amount of stars that has been mapped at any time before. And in years back, they will also look at the pre-stellar core and at the very faint protostar. And then in the second step, Ice Age will make use of the full wavelength to achieve JWST's with 40 to 28 micron. And we'll look at the evolved protostar and the protoplanetary disk in the ground with limit modes of JWST and Louis. And what we will hope to get are spectra from different stages of star formation, so we can actually see how the thermal history of the ice has evolved throughout the different stages of star formation in one cloud. And the spectra will be analyzed with a growing ice database. It has been investigated in the laboratory, and then the output from that program can be used for chemical modeling. And I just want to highlight the amazing capabilities of JWST in regards to astrochemistry in general. So again, here you can see what we will expect to see in the spectra of JWST. So you have, again, the 5 major ice constituents that I talked about earlier. So water, CO2, CO, ammonia, and methane, and also methanol and features of complex organic molecules. With Ice Age, we will be able to look at them over the full wavelength range of JWST from 2 to 28 micron, and we will also be able to map the ice in the clouds. And one of the major points for JWST is that we can observe multiple of those sources at one time, and we can also look at the composition of the ice as a distance to the protostar. And I just want to zoom in on the complex organic molecule feature at 7 micron here. So what you can see here in the bottom are spectra observed towards the protostar from 2 previous infrared missions. And at the top, you have spectra that have been obtained by laboratory experiments, so where you mix one complex organic molecule with water ice and then just obtain spectra to see how it would look like with liquid ice. And ISO has a highly sufficient resolution for some features, but spectra of this quality are only available for a very, very small number of sources. And the Spitzer instrument that we already heard about earlier, we won't be able to detect any of the COM features in here. JWST, we will have at least 25 times the spectral resolution and 50 times the sensitivity of Spitzer. So not only will we be able to detect the features in protostars, but we will also be able to detect the features in very, very faint sources compared to what was possible until now. And well, in a general picture of astrochemistry, let me just quickly talk about the pillars and also the 3 major pillars. So astrochemistry is a tight interplay between work in the laboratory, chemical modeling, and also observations. So for instance, in the laboratory, you can look at a molecule of interest and then quantify how it gets formed and how it gets destroyed. And those reaction rates can then be used to model that molecule in a more complex context. But also, if you want to analyze observational data, we need to know how we identify molecules in the spectra. So this is also where laboratory work is extremely important. But on the other hand, modeling or also observations can improve new ideas for experiments. And for models, it is also important to get some constraints of observations because we want to know how much of a molecule is actually in the environment that we observe, right? And so this is where this arrow comes from. And on the other hand, if reaction rates are well constrained from laboratory experiments, and if we have an idea about how a molecule behaves in a certain region from observations, then chemical models can be very, very powerful tools to predict, for instance, the physical environment in a region of interest. And this is a bit from our content. So I worked on observations and modeling, and my molecule of choice for the moment is methanol, and it's deuterated isotopolog, so it's heavy hydrogen isotopolog. And I am mainly looking at pre-stellar cores and young protostars, so the very early stages of star formation. And methanol and its isotopologs in those regions form in the ice. But as of today, we are only really able to observe them with gas phase facilities. So half of the picture, the observations in the ice are missing. This is not only true for my work, but for every astrochemist that is modeling ice chemistry of complex organic molecules. So yeah, it will be very, very exciting what JWST has to show us in that regard. And on a personal note, so I started my bachelor degree in 2013, and by then everyone was already talking about JWST and when it will arise and when it will actually launch with the data. I can't really believe that the day has finally come, and I'm super excited to find out what we're going to see in it.
From NASA, and before we take a short refreshment break, we will have the privilege of having Antonella Nota speak to us. She's the former head of the ISSI office at the Space Telescope Science Institute. And so she will be watering our mouths, for more to come. Please.
Thank you, Simon. Thank you for the nice introduction. And thank you also for organizing this wonderful event. It's so nice to see so many people here ready to celebrate. So I have to thank the previous speakers for covering most of the stuff that I will show you. But hopefully I will give you a little bit of a different perspective. Because as Tillman said, I was the project scientist for Webb for the last 5 years. So my perspective is slightly different, but I hope to provide you with new information that you haven't heard so far. So the first thing I want to say is pay attention to this. JWST is an international collaboration. NASA, ESA, and CSA exactly as Hubble was. CSA was not participating in Hubble, but they joined in for this one. ESA participates at a 15% level in this program. And that means that astronomers in Europe have guaranteed access to 15% of the observing time over the duration of the mission. This is huge, because in a sense, this is the reward for all the work that you put in building instruments and participating in all the processes that have led to the development and the construction of this amazing telescope. I cannot speak well enough of international collaborations and the value of international collaboration. It's really critical, especially in the current climate, to think that there is a venue, science and space astronomy, where communities work together, scientists and engineers work together, they solve problems, and they push science forward. So this is one of the takeaway messages that I want you to have with you. So it's a magnificent machine. We have heard already of how impressive, complex, and powerful this machine is. And part of the my take on the early release observation was exactly this. They were designed to show how powerful this machine is. And they were not designed to be scientifically useful observations. I will come to that, at the end of my talk. Although I can bet that there is already more than one astronomer in this audience that is writing a paper on the images that are coming out today. But it's it's so incredible to think the technology that went into this and the power. A mirror, 6.5 meter in diameter, the ability to look in the infrared. Pascal has just shows us a teaser, and Adrian as well. You are looking at mid-infrared imaging at Hubble resolution. This is just stunning, and so much science will come out of this. So Webb has been built for really ambitious science goals. We have already heard from Pascal about the distant universe. I want to stress a little more that our little Hubble, 2.4 meter in mirror, a small telescope, pushed our horizon. I really like the Hubble quote, all the way to 400 million years after the Big Bang. And Webb is going to push that window further, observing the first galaxies. Will Webb be able to see the first stars? We don't know. That's the challenge area. Astronomers are really hopeful that we will be able to see the first stars, but time will tell if the images that you will see in a minute, are the promise of what's to come, maybe yes, we will see. Other goals that are really important and have not been spoken to enough. You will see in the ERO images release that there is something to, to whet your appetite about what Webb will do on star studies. Webb will cover all the phases from the very beginning. Star formation, dear to my heart. I study young stellar clusters, and I'm dying to see my own observations of NGC 602, hopefully in the next year. And then the depth of the stars, planetary nebulas. And you will see today in the year of is one beautiful planetary nebula as it has been observed, covering the entire life cycle from cradle to death. Of course, when I look at this system, the TRAPPIST system, this is what I want to see Webb observing, because this is so similar to our own system in many ways, and to really find the composition of atmosphere around planets in a possible habitable zone will be just, an amazing scientific result. The 4 instruments that are on Webb will achieve this very complicated goal. 1.5 instruments provided by ISSI. NIRSPEC, the workhorse spectrograph. I think Adrian mentioned that this is, and Pascal as well, this is going to be a spectroscopic observatory. Most of the science will be done via spectroscopy. There will be beautiful images, but most of the science will be done by spectroscopy. And so the two, both NIRSPEC and MIRI will do, the heavy lifting in that area. Then we will have, of course, the imaging will be NIRCam, the US contribution, and then the Canadian instrument with specific applications on distant universe, GRISM observations, spectroscopy observation of distant universe, and exoplanet. And one of the EROs that you will see today is exactly that. The work the NIRIS will be able to do on exoplanets. You have seen this again, but I want to show, because we're never tired of just seeing the launch. It was totally spectacular. We're never tired to see, we're never tired to see the, this is too fast. Well, anyway. You have seen already the telescope detaching from the Ariane 5. One thing that you might not know is that traditionally there are no cameras on the Ariane rocket. This was especially done for this mission because people were thinking, wow, we really would like to understand how Webb is going to deploy and move into the final orbit. The orbit insertion was so crucial because that basically is what determined the lifetime of this telescope, among other things. And so when we effectively saw the solar array deploying, we were all standing in this Space Telescope auditorium watching. When we saw the solar array deploying before mission control could, we all knew that we were really in a good place because that command was a store command, was going to execute completely automatically only if the conditions were perfect, and they were. And so already at that point, you could see the engineers going around with big smiles on their faces because they knew that they had passed the 5 years lifetime goal, and they were probably going to exceed the 10 years. And now we know it's 20 plus. So I think that this has been absolutely amazing. You have already seen this deployment video. I just want to say a few words from the point of view of somebody who kind of lived every single moment of this deployment. This was the month of terror because you have no images, you have no cameras, you just rely on the telemetry to know that all the mechanisms are deployed. And they are so many, and I will show you in a slide in a minute how many of those mechanisms are deployed. And having lived through the ground-based testing, where not all the mechanisms are deployed and not all the non-explosive actuators had performed so well, this was just incredible. And it is testimony to the engineers who have been worked tirelessly to resolve all the little bugs and make sure that what they flew was perfect. And they knew that there was no second chance, because this thing goes to L2. We don't have Claude Nicollier heroes to go to save it. It had to work from day one, and it had to work flawlessly. So I will go, so this is just a summary of the mechanisms that I've actually deployed, just to give you an idea of why this was nail-biting in real time. 178 release mechanisms. I mean, this is no, we're not talking one. 178, 155 motors, 600 pulley assemblies. They all work flawlessly. So we can go, check, move to the next. And the next was this. And so the astronomers that I selected this isolated star to do the first alignment evaluation. They wanted an isolated star with nothing around it. It had to be an empty field. And when it was displayed, people started saying, but I see galaxies around it. I see galaxies around the star. And indeed, this image is peppered with galaxies. And the first conclusion was already drawn. There is no empty space with Webb. Wherever you look, you see things. So I can only imagine how the community will just dive in when the images and the spectra become available and start writing millions of papers. This will move science forward at an incredible pace. You've already seen this is the sharpness check, just to show that they were very methodical. The team in Baltimore was extremely methodical in the alignment of every individual mirror segment of the entire thing. You've seen, if you are on social media and follow the blog, you probably have seen the mirror selfies that were taken, that were showing how the alignment was going, how it was proceeding. And it was kind of amazing. And as I said, you look at 7 micron and you see the resolution of power. So really, really amazing here, and we'll see some more later on. So coming back to the arrow, which is what you wanted to hear, they were really, these observations were designed to wow. So not to be scientifically useful, although it will be interesting in 6 months to see how many papers have been generated by these images and by the spectra. The other thing that is important, keep in mind, back of your mind, so there was a committee that NASA put together with European representative, I was the one, and a Canadian representative. We worked for 2 years to assemble a list of possible targets. And we had to work not knowing what the launch date was going to be. And so we had to find targets throughout the year so that we had a full range. Once the date was defined, we could provide the list. And we had a few principles. So the first was not necessarily useful, but leadership. We have to stun the public. The second was we want to show the power of this machine. So we chose objects that we knew were going to shine in this exercise. We also wanted to show the synergy between the instruments. So when you look at what is published later on, you will see that for every object, not only we have the image, but we have the IFU, we have the spectrum that goes with it, because we wanted to show how the instruments really complement each other and enhance the scientific return from this telescope. And we really wanted to declare to the world, and I'm so proud that ISSI is part of this global network today that is really throughout the world to celebrate the fact that Webb is ready for science. This is NASA then decided a few days ago, after keeping a lot of everything very secret, to release the dates. The number of questions was going through the roof, and it was decided to just share the names just to avoid a potential leak. This was kept, I mean, people were asked to write non-disclosure agreements, people who worked on the data. It was so, and some of you know because you interacted with me when I was project scientist about what you can and cannot say, because the entire commissioning phase was kept really, the messaging was kept absolutely under control. But now, we can say that this is it. And the fact, I know that the US is very far away from here, but the fact that you have the President of the United States taking the time from the busy schedule between the worldwide crisis and another to actually unveil this image is really big and speaks to the impact that this project is already having on the world scale. And so I was very happy to see that Charles showed that map of Europe that we made after the proposal selection, because we thought that that was wonderful to show how Europe is involved and Switzerland is really involved in now exploiting the result of this work. And I think Pascal already has shown the link between the two. I mean, when you look at this Hubble and Webb comparison, we really were in awe when we saw the Hubble image. This is now like, wow. Somebody, you know, it is basically really impressive what the 6.5 meter mirror does, the difference that it makes. And of course, in the US, they're pulling all the stops to this. Just the celebration are endless. Tonight, if you just look at the camera on the Empire State Building, it will be turning gold to celebrate this day. So with this, the only thing that we can say, are you ready? Because in a few minutes, we will see this magnificent data.
Skywatchers, this is it. This is the day we get the first science images back from the James Webb Space Telescope, and you've got a front row seat to the cosmos. I'm Michelle Thaler, your host for what can only be described as a celebration for everyone on Earth. So think about this. Light from the earliest days of the universe has been traveling to us for billions of years. Just over the last few weeks, we've captured some of that light with a telescope that sees the universe in an entirely new way. And today we share the very first results. So longtime space fans are going to know who this is. This is Dr. John Mather. He's the senior project scientist for the Webb telescope and a Nobel Prize winner. And John, I couldn't be happier to be here with you today.
Thank you. It's a thrill to be here for this very special day.
How are you feeling?
I am thrilled and I'm relieved because you know when you start something this big, you know there's always a possibility it might not work. It did work. We are so proud.
And you've been on this project for a very long time, right?
Yeah, started in 1995. We had just finished measuring the Big Bang. We measured it with a Cosmic Background Explorer satellite that we built right here at Goddard. And we measured the spectrum. We measured there are hot and cold spots in the Big Bang. So we said, now we know it all, how it all got started. But then what happened after that? So then I got a call from NASA headquarters. Would I like to work on this new telescope that's going to help answer those questions? What happened after the Big Bang? How did the galaxies grow? How did the first black holes grow? What happened all the way from there to here? So this is our time machine, and I just wanted to be part of it. I am so thrilled that we got a chance to do it.
You know, one of the things that I remember you saying, and this is kind of amazing, that after you win the Nobel Prize, you thought that this mission was the most important thing to work on.
Absolutely. It's the next question. After you know how it started, what happened then? And you know, suddenly we now have the technology to do it. We didn't have 50 years ago. We didn't have the technology 25 years ago, even when we started this. We had to invent things along the way, so we did that, and here it is.
Well, thank you. We'll be back to you in just a moment. So at the moment, we're going to talk about the way that Webb is a completely new way to explore the universe. So today, the mission releases its first science images and gives wings to the dreams of so many people who worked so hard for so long to make this possible. For everyone on Earth, this is your telescope. This is the largest, most powerful observatory ever put into space. It's the product of thousands of people working for more than 2 decades. This is a mission that's singularly focused on the biggest questions in science. So the following phrase is often used too easily, but today actually does mark the dawn of a new era. Today, the Webb mission is open for scientific business, and this is just the beginning. The best is yet to come. So, John, one of the things you told me about is that you really want to make sure there are some people that get thanked, people that put a huge amount of effort into this.
Absolutely. Our current project manager, Bill Oakes, took the project from a time of trouble when we didn't exactly know how we were going to get this to work, and got it all the way to the end. Here it is working, and it's because of Bill made this worldwide team. 20,000 people around the world were involved in making this thing all work, and Bill has been there every day making sure that it would happen. So other special person is Senator Barbara Mikulski. She saved our telescope, and she saved the telescope before us. She made sure after the Hubble telescope was launched and it was not in focus that we would go up and fix it. She made sure that happened. When the Webb telescope needed more resources, she made sure we could get that. So Barbara, we thank you.
Well, it's such an honor to be with you, Jay. I mean, it's been a pleasure to be working with you through this whole thing. Thank you so much. Congratulations, and go Webb.
Thank you.
So this broadcast, much like every part of this mission, is a partnership. On our journey to explore distant places in space, we've been joined by intrepid travelers from around the globe. We have so many extraordinary collaborators. So let's check in with our partners who will be sharing the stage with us today as we reveal Webb's 5 first science images. From the European Space Agency, I'm joined by Katie Haswell in Darmstadt, Germany. Katie. I see Katie in the background there. Also joining us from the Canadian Space Agency in Montreal, we have Natalie Willette and Sarah Gallagher. Bonjour. I see Katie in the background there. I see the waving too. And so naturally, we're also going to be visiting the nerve center of this mission, the Space Telescope Science Institute on the campus of Johns Hopkins University in Baltimore, Maryland. And there we have Alex Lockwood and Carl Gordon, and they're going to give us updates and more. Good morning. Great. So we'll be back with our international partners shortly, where they'll each reveal one of the new images. But today we're also going to be joined by millions of science fans from around the world. Many are gathered at watch parties just for this event. So here we are really going international. So I'm beginning with Bhopal, India. Do we have a signal from Bhopal? Yes. Excellent. Welcome to NASA. Hello, everybody there. Wonderful to be talking to you today, all the way in India. We'll be back to them later, yes? Great to wave to you. Hi, wonderful. And we also have a warm welcome now in Portland, Oregon. So we have the feed from Portland. A bit dark, but I see everybody there. Hello, Portland. They're in an auditorium, I see. Okay, next we're going to go off to Milan, Italy. So afternoon in Italy. Do we have the feed from Italy? I guess we have a screen from Italy. And next we're going to go to Rutland, Vermont. So is this Vermont? Hello, Vermont. Hi, everybody. Nice to see you. Thank you for being part of this today. Okay, going even a little bit further afield, we have Netanya, Israel. Hello. Hello, Israel. Yay. Really nice to see you guys. Okay, and just one more for now. I see people like giving me hugs. Okay, we also have Vancouver, Canada. Hey, Vancouver. Hi. All right. Wonderful. Wonderful to have all these people with you. So right across from the campus from me, there's also a huge watch party taking place with members of the Webb team. So the wonderful thing is that they actually are people that have worked on the mission, and they are part of our NASA Funny family. So hello Webb team. There they are. Yes. A lot of people I recognize there. So it's incredibly important to me personally, and also to all of us at NASA, that the universe belongs to everyone. And we are thrilled to share this day with fans everywhere around the world. We'll say hello to some more later in our broadcast. So now it's time to start the main event. What you'll see over the next hour will be a collection of images newly processed by the Webb science team. Only a tiny handful of experts have seen the images so far, and I can tell you that we have been so excited to unwrap them for everyone. We will be releasing each image in turn in real time. As soon as you see it on this broadcast, it will be available for download on the internet. On the screen below, you can see a timeline showing where we are in the show and what's coming up next. And by the end of the show, all 5 images will be available to everyone. So hopefully you can tell I'm excited. Okay, so let's do this. Okay, we're going to release the first image right here at NASA Goddard Space Flight Center, Maryland, and we're just outside of Washington, D.C. NASA Goddard is home to the project office of the Webb telescope, and the observatory portion of the telescope, the mirrors and the science instruments, were integrated and tested here before launch. So for many of us, including myself, seeing Webb come together bit by bit right in front of our eyes was an emotional and very inspiring experience. So it's kind of like a part of us was out there with Webb right now. 1 million miles away, part of our hopes and dreams are out there. So I'm joined now by Jane Rigby, the operations project scientist for the Webb mission. And she's a familiar face for people who've been following this before, so welcome, Jane.
Hi, Michelle.
Okay, so Jane, you not only get the honor of revealing the first image, but this actually got a little bit of a sneak preview. I understand there was a very select audience who's already seen the image.
Yes, so last night, on behalf of the project, I had the privilege of traveling to the White House with the NASA Administrator Nelson and other senior staff to share our first image with President Biden and Vice President Harris. And it was really fun. Oh my gosh. They really geeked out. We had a closed door session where we got to walk through all the images and just share the excitement, and they were so thrilled and they got the profundity of what we're seeing. And so now let's do it.
Okay, we've got the whole world watching. Are you ready to put the first image up?
Oh, let's do it.
Absolutely. All right, here we go.
Okay, so the first image is a deep field, and it's also a deep field with a cluster. So why don't we walk through this just a little bit? So if we come up and look at this image, first of all, it's really gorgeous, and it's teeming with galaxies. And that's something that has been true for every image we've gotten with Webb. We can't take blank sky. Everywhere we look, there's galaxies everywhere. And so, this image, as we're looking at it, what we're seeing is not just all the galaxies, but there's a cluster here. And so the cluster are all these white, kind of ethereal galaxies. We're seeing them as they looked back in time. Right? The speed of light is only so fast. And so as we're seeing distant galaxies out in space, we're seeing them as they looked billions of years ago. So these cluster galaxies, the white ones, we're seeing as they looked about the time the sun and the earth formed. And then behind the cluster, we have the gravity of the cluster is distorting and warping our view of what's behind. And so there are these galaxies that look stretched and pulled, kind of like they've been magnified because they've been magnified by the gravity of the cluster, just like Einstein said they would. And it's really, there's so much detail here. We're seeing these galaxies in a way that we've never been able to see before. There's just a sharpness and a clarity we've never had. And so we can look at, if we zoom in on this image, and I encourage you as you grab this image at home, zoom in. You can really zoom in and play around. There are galaxies here in which you're seeing individual clusters of stars forming, popping up just like popcorn. And then we also see in the background of this image, kind of littered like jewels all over the back of the image are these faint red galaxies. Now, that was what we built the telescope to do. The most distant of those are billions of years. We're seeing as they looked more than 13 billion years ago. And so galaxies like that one right there, this little red guy, you're like, okay, yep, what is that? Well, Webb got spectra to figure out what those galaxies are made of, and this is that one. We're seeing as it looked 13.1 billion years in the past, less than 1 billion years after the Big Bang. And we're seeing the elements of oxygen and hydrogen as well as neon. This is how the oxygen in our bodies was made in stars, in galaxies, and we're seeing that process get started.
Yeah, I want to give this a little bit of context. So this is now the farthest away galaxy that we have this sort of detailed information about.
That we know what it's made of.
We know what
like
it's
that.
made of.
Yes.
And this was not a long exposure for Webb.
No, the previous record holder, right, the Hubble Extreme Deep Field, was 2 weeks of continuous work with Hubble, and it was just imaging. With Webb, we took that image before breakfast. The amazing thing about Webb is the speed at which we can churn out discoveries. So everything that you're going to see here in this broadcast is a week, and we're going to be doing discoveries like this every week.
That is absolutely incredible, Jane. So thank you so much for joining us. It's been an honor to be working with you. Congratulations on all your hard work.
Thank you. It's so wonderful to see it pay off.
So thank you, and I'll see you later on today, I hope. So
Yes.
enjoy the day.
Thank you.
Right. So from distant galaxies, we now turn our eye to something a bit closer. It's a planet, but not one in our solar system. Remember that Earth and its sibling planets aren't the only show in the universe. When scientists and engineers started developing JWST, the search for exoplanets wasn't even part of the plan. That's changed. Exploring exoplanets is now a major component of the mission and the subject of our second big reveal of the day. I'm going to send it now to our friends Natalie Willette and Sarah Gallagher at the Canadian Space Agency in Montreal. So again, bonjour. I guess we're having a little. We'll go.
Okay. I'm Nicole Webb, and I'm here to tell you.
Sorry for the brief pause there. We're now going over to Canada. Okay. Yep, we're all ready. Yeah. Okay, I apologize. We're having some trouble with the signal from Canada, but luckily for us, we have an exoplanet expert right here, just in case that happened. So this is Nicole Colon, and she's an exoplanet scientist at NASA, and we're going to talk about this amazing new result from a very hot planet, I understand about 1,000 light years away.
That's right. The exoplanet is named WASP 96b, and it is this hot, gaseous, giant, puffy planet that it is about 1,000 light years away. So that's why today's release is so exciting, because it teases at what Webb is able to do for such a distant planet.
Absolutely. So talk us through what this discovery is and why this is so significant.
Well, this reveal that you're going to see is going to show the first spectrum of an exoplanet as taken from the Webb telescope. And this is exciting because it covers infrared wavelengths of light that we have not had access to before. So we've been able to use other telescopes to explore exoplanet atmospheres in the infrared, but not to this level of detail. And this is just one sliver of data that Webb is providing us using the nearest instrument specifically.
And there's something about infrared that is actually particularly good for the spectrum. So in this case, what we're doing is we're actually going to take the light and break it up into a rainbow and look very, very carefully at how much color is coming in each part of the spectrum. So I believe we have that image, if we can put that up.
Okay, yes, I believe we're revealing the spectrum right here. So we now have our spectrum, and this is exactly what you're seeing. As you just described with spectroscopy, what we did was we observed a transit of an exoplanet. We observed the planet as it passed in front of the star. Now, mind you, this is not a direct image. This is an indirect image. So we've seen the effect of what happens when the planet and its atmosphere passes in front of the star. The starlight filters through the atmosphere, and then you can break that down into wavelengths of light, and you get a bunch of what looks like bumps and wiggles to some people, but it's actually full of information content. So you're actually seeing bumps and wiggles that indicate the presence of water vapor in the atmosphere of this exoplanet.
So we have the spectrum up here. Is there anything you'd like to highlight particularly?
Yeah, absolutely. So we have several features marked here. So I call them features. They're these, what I just referred to as bumps and wiggles. But what you're seeing here is a telltale signature, the chemical fingerprint of water vapor in these atmospheres, in the atmosphere of this specific exoplanet. And the other thing we can tell actually is that there's evidence of clouds and hazes because the water features are not quite as large as we predicted. So we can take that and infer that there are presence of clouds and hazes.
Right. Now, one thing that we really want to make sure people understand is with this particular planet, this is a hot world. It's actually closer to its star than Mercury is to our sun. And so we're not looking at liquid water here. But we're looking instead at sort of steam, water vapor.
Yes, this is an exoplanet. It's about the size of Jupiter, about half the mass of Jupiter. It orbits around a sun-like star, but it does it every about 3.5 days. Right. So it's extremely hot, extremely close in, nothing like our solar system planets. But that's okay, because what we're seeing is, again, the first exoplanet data from Webb, and this is just the beginning. We're going to start pushing down to further smaller planets and being able to take measurements just like this with the NIRS instrument that was built by the Canadian Space Agency, but also there's three other science instruments that will add to our knowledge in the infrared, as well as direct imaging modes along with the transit method. So there's a lot more to come.
And I guess one thing we should mention is not only are we going to be looking at planets that are more like the Earth in the future, but we'll also be looking at planets in our own solar system.
Absolutely, yes. We're going to have exciting data from planets in our solar system, from Mars outward, as well as asteroids and comets. So stay tuned for a lot more to come.
Thank you so much, Nicole. Thank you so much for telling us about the spectrum, and I'll be seeing you later on today. So we have 3 more big image reveals, and with that, new and more exciting science. But first, let's take a look back at the journey that brought us to this moment. Celebrations like this one are only possible with years of hard work from a cast of thousands. When a new mission is being built, even the most enthusiastic space fans only get to see dramatic moments in its life cycle, the news and images that come out in updates and press releases. But that doesn't really give you the sense of the huge effort that goes on behind the scenes every day. The plans, schedules, and organization to keep everything moving forward really happens, for the most part, out of people's gaze. Webb started as an idea that took root at NASA Goddard. It grew first into planning teams, research projects, schematics, requirements. Then it began the long journey to become real with the development of new technologies, cutting-edge engineering, and finally fabrication, putting it all together. Let's take a brief look back at the visionary journey to how we all got here today.
So today was the final closeout of the purge.
Okay, guys, I can hear Rupa,
It's a pretty emotional moment to be in there and actually, closing it up for the very last time, right? You're the last one to touch this, and so that was the final operation. And once that fitting is closed out, there's no more touching of the vehicle. We're ready for launch.
The James Webb Space Telescope. Born from the desires of astronomers, achieved with newly invented technology, is the culmination of 20 years of work. Humanity has unlimited questions about our universe. Engineering a way to investigate them requires enormous creativity.
Webb has been a trade-off between engineering performance, what the astronomers want, risk. In fact, when we started 20 years ago, we were actually looking at an 8-meter telescope.
Developing the most sensitive instruments. And testing, and more testing.
And so you don't want to build one that's just incrementally better than what you've got. Because if that's the case, you would just observe longer on the telescope that you already got. And so every time NASA builds a new astrophysics mission, a new telescope, it needs to be way more sensitive, way more capable than anything we've ever built before.
We all got together in that conference room and we played real time as the images came down from the spacecraft. The very first diffraction limited images ever obtained with Webb, and what we collectively saw as a group was the highest resolution infrared image taken from space ever.
If you're just joining us, I'm Michelle Thaler at NASA's Goddard Space Flight Center, and you are watching live coverage of the release of the first science images from the James Webb Space Telescope. So it's appropriate now that I send the broadcast to our colleagues and friends at the Space Telescope Science Institute in Baltimore. That's the scientific nerd center of the entire Webb mission. So hello, good morning, Alex. The show is yours.
Hey, Michelle. Welcome to the Space Telescope Science Institute. I'm Alex Lockwood, and I'm here with Carl Gordon, who is an astronomer and one of the key people in delivering the images that you're going to see here today. But actually, before we get into the amazing images, we're going to talk a little bit about where we are. We're standing here outside of the Mission Operations Center, which is the key central hub for Webb. For the past 6 months, scientists and engineers have been working 24/7 since they took control of the telescope 30 minutes after launch to prepare for today and for the amazing science to come. Through all of the major deployments, focusing, aligning the telescope, and calibrating those 4 amazing science instruments, it was all done in this building. And from here on out, we'll have daily communications with the telescope, including sending commands and downloading data with the help of the Deep Space Network. In addition to mission operations, we are also the home of science operations. Well, what does that mean? Every year, we solicit proposals from astronomers across the country and the world for what they would like to look at with Webb. Then we hold a rigorous selection process to select the ideas that will best utilize Webb to study and understand our universe. When the data come down and astronomers analyze their results, we are the lucky ones who get to share that data and those amazing science results with you. And we knew that today was going to be so exciting with the first images, so we've actually been preparing for years. Here is Klaus Pontoppidan, project scientist for Webb and the technical lead for the first images,
it's been a year
to tell you about the process of the past few
I look back
years
and
of
my first
selecting the
email
targets.
related to the first images was back from 2016. So back then, a committee was created, and this committee was charged with coming up with a long list of targets for the first images. And the reason for that is that the observatory can't see the entire sky at any given time. And this is because you want to avoid the mirror seeing direct sunlight to keep it cold. And it actually had to be quite a long list. We ended up with about 70 targets, from which we had to select only a handful. You know, what would create the most beautiful images, what would highlight the instruments, the different 4 science instruments for Webb, and what would highlight the 4 major science themes for Webb. And it's a celebration as well of the beginning of science observations.
And we knew that selecting the images was just the beginning, that we would need a trained eye to take these exquisite data and pull out the beauty and the science potential. So here's Jody Pasquale and Elisa Pagan to tell you about how they processed these beautiful images. And they have it up downstairs. I think they missed some of that beginning.
We're basically translating light that we can't see into light that we can see by applying color like red, green, and blue to the different filters that we have from Webb. And the reason we want to color the images is because there's actually more that you can get, more information that you can get from the image if you see it in color.
So it's a matter of picking and choosing filters and colors that enhance the details and the structure in the image itself.
The shortest wavelengths of infrared light and assign those blue colors, and then move our way down to green and red as we go to longer and longer wavelengths.
And then we additively combine those together to get our full color image.
But there is a lot of aesthetics that are involved in this. Painstakingly going through and cleaning these images up with an attention to detail, a level of detail like at the pixel level in every image.
So when I'm working on the astronomical data, it is this sort of marriage between art and science. When you're choosing colors for the filters, you really are trying to show the different details and the processes that are happening in the astronomical images. But at the end of the day, you want it to be very compelling. You want it to be very beautiful because space is beautiful.
And after those images were processed, there was a select few of us, very lucky few of us, who got to see the first images.
So this is downscaled by a factor of 4. Exactly. So just to make it a little more handy, so it's actually high resolution. So we have a team of about 30 people who are producing these images, and we feel incredibly privileged to be the ones who are the first to see these science-like images. When we saw the first data come down of real targets, people were speechless and there were emotions, because we could see how amazing this observatory will be. The detail, the sharpness, the depth. And when we saw the first color images, we knew that we had a winner.
And now we are ready to see Webb's first image of a star dying, a planetary nebula called the Southern Ring. Let's do it.
Oof.
Wow, wow. This near-infrared image is, wow, the detail. Oh. Wow, okay, well, here we are. We have a near-infrared image on our left, or on maybe your right. And here on the right, we have a near-infrared image. And so I'm here with Carl, our astronomer specialist. Can you tell us what we're looking at in these images?
So this is a planetary nebula. It's caused by a dying star that has expelled a large fraction of its mass over in successive waves.
Okay, so we actually see those waves in these images.
Yes.
Wow, wow. And so there's a lot of structure. Can you tell us a little more detail about what we're looking, maybe start with this one on the left?
Yeah, so in the NIRCam image, you see this kind of bubbly, almost foamy appearance throughout the whole nebula with some very structured shells. And this foaminess is showing up in orange mainly. And this is due to the molecular hydrogen that's newly formed in the expansion, just lighting up the gas and dust of this nebula. And then as we move inward, you see this kind of very blue haze in the inner region. And this is actually due to very hot ionized gas that emits well in the blue that's heated by the core, the leftover very hot core of this star.
And what about these like rays that I'm seeing in this image?
Right there. So there's also rays in the outer regions that you can kind of see, and these are holes in the inner nebula that are actually allowing the central star's light to come out and kind of light it up like patchy clouds with the sun shining through.
Wow. Oh, yeah, that's what it looks like. That's so cool. So you're actually a mid-infrared astronomer, which is different than near-infrared. And so what can you tell us about the details in this mid-infrared image?
So it looks quite different in color, partly because we're seeing different kinds of physics going on here. So we're actually seeing in the blue, you see a lot of blue. The blue is actually due to hydrocarbon grains that are emitting very strongly in the blue for MIRI. And they show the very similar structures to what we see in orange and NIRCam because the molecular hydrocarbon actually forms on the surface of dust grains. And so again, as we move inward, we see that the inner region is again hot ionized gas, but now it glows red because that's where it emits the strongest for MIRI wavelengths.
Okay.
And then as we go into the center, we see kind of the surprise for us, which is we knew this was a binary star, but we effectively didn't really see much of the actual star that produced the nebula. But now in MIRI, this star glows red because it has dust around it. So in MIRI, we got to see both stars very clearly.
Yeah, you can't see it in the first image really, but there's two stars there. So that's a fun surprise. And I think that there's another little Easter egg you want to tell us about?
Yeah, so this was, the Easter egg is this kind of narrow filament up in the top that's radially aligned. You can kind of see it very clearly in the MIRI image. It shows up as this blue structure. And it points very much to the central sources. So I thought, oh, this must just be a density enhancement in the outer nebula. I thought that very, very strongly, but other people on the team were like, no, it's a background edge-on galaxy. Well, I made a bet that said, no, it's part of the nebula. By the way, I lost the bet because then we looked more carefully at both the NIRCam and MIRI images, and it's very clearly an edge-on galaxy with a dust lane and a bulge. So I lost the bet.
Well, you lost the bet, but you got these gorgeous images, so I think it's a win for everybody. Anything else you'd like to say today?
I can't wait to see where we go from here.
Neither can I. All right. Thanks so much. Back to you, Michelle.
Thank you, Alex and Carl. And I have to say that image is absolutely spectacular. So as you know, people from all over the world are watching us today and joining in our excitement as we release Webb's first science images. We've been checking in with our colleagues in Europe and Canada throughout the program, but we also want to take a moment to include the people at the so many viewing parties scattered around the world like stars in the night sky. So let's check in with some of them now. First, we go all the way to Perth, Australia. Do we have a signal from Perth? I guess nothing from Perth right now. Maybe we have some of our other feeds. We're going to check in with them right now. Do we have Winnipeg, Canada? Oh, there it is. There's Australia. There's Perth. Hey, waving to Perth, Australia. Thank you so much for joining us today. And next we're going to Winnipeg, Canada. Hello, Winnipeg. At a planetarium. Everybody's enjoying the show, I hope. Okay, Dayton, Ohio. Everybody's watching on the, there we go, Dayton, Ohio. Hello, everybody, Dayton. Nice to have you here with us. There we go, yes. Hey, hey, Dayton. Hey, they're jumping up and down. Hi. Okay, all the way Bangalore, India. Bangalore. Hello, hello to Bangalore, India. Hey. That's absolutely wonderful. Hey. Okay. So I hope you enjoy the rest of the images we're releasing. Okay, of course, NASA's family extends all over the country. The team at JPL in Pasadena, California, they're on site to celebrate with us. So hello, JPL! Some of my favorite people in the world. Hey, hello! And then I think the last place we're going to right now is Northrop Grumman, one of our major contractors. Hello, Northrop Grumman! Oh, hey, all right! Yay! Nice to see you, Northrop Grumman. All right, now there's also a big watch party right here on the NASA Goddard campus. Many of these people have worked on the mission itself, and we also have top NASA leadership and representatives from our government. So hello, hello watch party at Goddard, yay! Okay, wonderful. So, I mean, at NASA, we are so fortunate to have all of these friends and colleagues around the globe. A major partner in the Webb mission is the European Space Agency. ESA contributions have been essential to so many aspects of this project, including Webb's spectacular launch on the Ariane 5 rocket last December. I'm very pleased to turn over the show for a few minutes to Katie Haswell. She's joining me from the European Space Operations Center in Darmstadt, Germany. Hello, Katie. Good afternoon.
Thanks, Michelle. Thank you, Michelle, and welcome to Germany. We're at the European Space Agency.
I'm still getting all kinds of IFB from lots of
Center. It's where the teams effectively fly the satellites. They're a little bit of a cross between air traffic controllers and pilots. We have lots of different control rooms here. This is the main control room, and as you can see today, it's not in use, so we've been lucky enough to move in here for today. I have two very special experts with me, both scientists from the European Space Agency. Giovanna Giardino is a near-spec scientist. Giovanna has been working on that for many years and lots to tell us about that. And Mark McCaughrean is a special advisor for space, for science and exploration. These two guys have been working on the Webb Space Telescope for a long time. So we're very grateful to have you with us. Thanks, folks.
Pleasure.
We are excited to reveal our image with you. But before we do that, we thought we'd give you a little bit of background, because we've come here today because these guys were the first ones to pick up the signal during the Webb launch, when Webb first launched. They run a system called S-Track, which is NASA's deep space tracking system, and they were listening out when Webb called home. And the controllers here have been looking after a whole very, very impressive list of missions since 1968. ESA has played a very, very important role during the Webb for the Webb Space Telescope. They provided the launch on board the awesome Ariane 5 launch vehicle from the Guiana Space Center. The atmosphere in the Mission Control Center was electric, I can tell you, I was there. They've also provided people. We have 15 ESA scientists working at Space Telescope in Baltimore, and also they have provided the infrared spectrograph, the near-infrared spectrograph, and also half of the MIRI instrument, which is the mid-infrared instrument. Let's take a look at those now.
Webb's 4 scientific instruments include NIRSPEC, the near-infrared spectrograph led by ESA. NIRSPEC splits near-infrared light from astronomical objects into its components. Like a barcode, this will help scientists understand the physics of the objects they're observing, from their temperature to atomic makeup. NearSpec can observe parts of an object or the sky using an image slicer and an array of microscopic shutters. Webb's integrated science instrument module, located behind the main mirror, also contains MIRI, a mid-infrared camera and spectrograph. Seen here during testing, MIRI's been developed by a partnership between Europe and the US. MIRI detects mid-infrared light from planets, stars and galaxies. It can analyse molecules to help us deduce what astronomical objects are made of and peer into clouds of gas and dust where stars and planets are born. Together, these instruments will help Webb detect and analyse light from the very dawn of time, revealing the universe as never before.
So let's get ready to reveal our image. And remember that one of Webb's jobs is to find out about galaxies, more about the galaxies, but also to help us to understand how they change. And this image is going to be very, very useful for that. Let's reveal it now. There it is. It's called Stephan's Quintet, and it's wondrous. Giovanna, what are we looking at?
Yes, like it's a quintet, so we are looking at 5 galaxies. Galaxies are this giant structure that, as we've seen, we see everywhere around us in the universe. They contain from million to 100 billions of stars, and in fact we live in one of them, the Milky Way. And here we see 5 of them. This is a closer galaxy in the foreground, and these 4 are at a distance of about 300 million light years from us, and are locked in a close interaction, a sort of cosmic dance driven by the gravitational force. You can see here these two in a process of merging within each other. This is a very important image, an area to study, because it really shows the type of interaction that drives the evolution of galaxies. That's the mechanism of galaxies' growth.
I love this image of the cosmic dance moving through each other. Mark, there's a lot going on, though, in this image, isn't there?
There is. So this is a near-infrared image and a mid-infrared infrared image combined. And when we zoom in on the left-hand side here, we see this foreground galaxy. We see lots of individual stars in there, actually resolved as point sources, which is remarkable. And then as we pan across, we actually see the galaxies in the merging galaxies. We now see gas and dust, which is being heated up in the collision between those galaxies. And that's a place where new stars are being born today. So we're actually seeing the process of creation of new stars in this region. And then when we look in the background here, we see not only the galaxies at 300 million light years, but also stars in our own galaxy. These snowflake structures that you see here, those are nearby stars, but in the corner and around the edges, we see galaxies which are much, much more distant, much further away. So similar in some sense to the ones that we saw earlier on in that deep field. And so this image actually takes us from the nearby galaxy, our own Milky Way, through these galaxies which are evolving today, all the way to the distant universe. And in a way, it captures cosmic evolution of galaxies over those 13.8 billion years.
So we have another image, don't we, that we can
exactly.
look at?
So if we strip away the near-infrared view there of the stars predominantly, now in the mid-infrared with MIRI alone, we see mostly gas and dust. So we see the same galaxies again, the two merging, and then we also see something very interesting up at the top here, because this top galaxy has something new and bright in the middle of it. And Giovanna, tell us what that is.
Yeah, that's an active black hole. We cannot see the black hole itself, but we see the material swirling around, being swallowed by these sort of cosmic monsters, and this gas gets heated to extremely high temperature as it falls onto the black hole, and it becomes very bright. In fact, this is how shiny is the galaxy. Here we see luminosity that are 40 billion times the luminosity of our suns. It's really, really bright. And with NearSpec, we can zoom into this area, and we have this technology that allows us to take thousands of images at different wavelength channels, so see the this distribution of the gas, what's going on in the gas in different regions of this core area, and understand the composition of the gas, the velocities, the temperature. So that's very important to understand the physics.
So
of
it's
this
giving us
object.
so much information, and it just shows the power of this telescope. Mark, this is just the beginning, though, isn't it?
I think that's a very important takeaway from today. You know, these are like pictures just taken over a period of 5 days, and every 5 days we're getting more data, which will contribute more in that direction. It's a culmination of decades of work, but it's just the beginning of decades. And you know what we've seen today with these images is essentially that we're ready now. This telescope is working fantastically well, and you know, to borrow a phrase from a famous rock musician, you know, we're ready to turn this telescope up to 11. It really is time. It's fantastic.
Thank you very much indeed, both of you. Back to you, Michelle.
Thanks, Katie. It is so great to have you and your colleagues with us on this historic day. So before we get to the fifth and final image reveal of the day, it cannot be said enough that an achievement like the James Webb Space Telescope is something bigger than any one of us. It's bigger than any organization, any country. This truly takes a planet. Webb belongs to all of us, and starting today, the discoveries start and they're not going to stop. This is just the beginning. We've said several times throughout the broadcast that the Webb mission is about people, and during the construction of the Great Telescope, people started to see themselves in it, literally. Day after day, people visited the observation window at NASA Goddard, and looking through the glass, they snapped selfies of themselves reflected in the gigantic golden mirror. These photos are actual reflections of the enormous human investment and the emotional commitment that brought this mission to life. And now, years later, that mission is finally collecting light from the earliest days of the universe, all the way to worlds in our own solar system. It's the same mirror that reflected the many faces who see themselves as part of the journey to understand our shared origins. Let's stop for a moment and appreciate the people behind Webb. Okay, it's time now for the last image to be revealed. Here we go. So Amber Strawn is Webb's deputy project scientist. She's here with me today to share the final big reveal of the day. So Amber, it is so good to see you. How are you feeling?
Oh, so great, so exciting. What a great day this is.
Yeah, so one of the things that we're going to do is before we get to the final image, the James Webb Space Telescope has taken us all over the universe today. So let's do a quick review of where we've been so far. So Jane Rigby got us rolling today with an extraordinary new deep field image, showing us one of the farthest views of the universe ever.
Yeah, this image really does demonstrate that JWST can do exactly what we've designed it to do.
Yes. And the Canadian Space Agency then took us to the massive planet WASP 96b, where the team has detected evidence of atmospheric water.
And here again, we're seeing the incredible efficiency of this observatory. We're able to do these kind of measurements in a fraction of the time that we're able to before.
And then we zipped up the road from NASA Goddard to the Space Telescope Science Institute, where Alex and Carl showed us the exquisite Southern Ring Nebula, a mixing bowl of stellar matter around a pair of dying stars.
Yeah, and I'm just blown away by the level of detail we can see, like in the outer part of this nebula. It's incredible.
Wow. Okay. After that, it was off to Germany, where the European Space Agency wowed us with pictures of galaxies interacting and mixing together.
Right, and this image, again, it's incredible because it's showing us one of these fundamental processes of the universe, how galaxies merge together, and we're able to learn about these processes in a brand new way.
So the Webb team has a lot to cheer about right now. So across the campus, there's this big watch party, and we can feel the excitement all the way from over here. So let's join that celebration now. We're back with Senior Project Scientist John Mather, along with the head of NASA's Science Mission Directorate, Thomas Zurbuchen. Hello.
Hey. So, John, we looked around the world and we're the only ones with a cheerleading crew right over there. That's amazing. Look, you've been with this mission for decades. How do you feel today?
I am so thrilled and so relieved. This was so hard, and it took so long. It's just impossible to convey how hard it really was. That we risked so much to say we're going to go do this, and it's so near impossible, but we did it.
Yeah, there are thousands of ways this can go wrong.
Yes.
Many of them, we worried about and frankly feared even after launch. I have to tell you, I was really, really nervous. And, it's almost like athletics for me. You always get to know the team when they're on the field. And on the field, they were right after this launch, and they were perfect.
They absolutely were. And I really wasn't worried, but maybe I should have been.
Yeah, that's difference between the two of us. I always worry. I always tell everybody I'm paid to worry, frankly, and that's good. What we want to do, though, is, just really thank the team again. Of course, we heard Bill and Scott and Greg talking about the team that is there. I think what's also important is to recognize that Bernie is sitting there, who was the first manager. I was sitting there. Could you stand up? And I want to mention that Phil Sabelhaus, who is a manager also during that time, is no longer with us, but his heart is with us today.
Yeah.
I have to tell you, John, after each one of these milestones, I called a lot of people. I called Bernie, for example, and I called people who at my job and people who are administrators, because there's many of them. And I just wonder how you feel about the team. Just give you the word here.
I am just so thrilled that we had a privilege to assemble such a brilliant team. We drew from the best of the best, and here we are. So my extreme deep thanks go to all the people who built that team, not only to Bernie, who started us and helped us build up all the technology, to Phil, who made sure we would have a plan, and then when we didn't have quite enough money, to Bill, who pulled it all together and made it get all the way to the end. I am so thrilled that we had so much talent to draw on. And here we are, we have the support of the country and the world to take on this immense challenge.
You know what I'm most excited about? There's tens of thousands of scientists, and frankly, some of them just got born, or not even born, who are benefiting from this amazing telescope, because it will be with us for decades.
It will be. It took us about 25 years to get here, since 1995, and we have at least 25 to go, I hope.
So look, we are in a sense of these images, the art that is out there in the sky, revealed for the first time. We're thinking of the team and we're thanking them. John, thanks to you, thanks to all of you, and back to Michelle.
Thank you so much, Thomas. And this entire collection continues to just absolutely astound me. Okay, Amber, so here it is. Can you walk us through the final image reveal?
Absolutely. Here we go.
The last image is, wow, look at that. So Amber, can you tell us a bit about what we're seeing here?
Of course. This stunning vista of the cosmic cliffs of the Carina Nebula reveals new details about this vast stellar nursery. Today, for the first time, we're seeing brand new stars that were previously completely hidden from our view.
There's something you want to point out here?
Absolutely. So honestly, it took me a while to even figure out what to call out in this image. There's just so much going on here. It's so beautiful. One thing that really stands out to me is you sort of get this sense of depth and texture from this new data. There's a lot going on. To call out a few specifics, first of all, in general, the Carina Nebula is a nearby star-forming region within our own Milky Way galaxy, about 7,600 light years away. And in this view, we see some great examples, first of all, of hundreds of new stars that we've never seen before. We see examples of bubbles and cavities and jets that are being blown out by these newborn stars. We even see some galaxies sort of lurking in the background up here. We see examples of structures that, honestly, we don't even know what they are. Like, what's going on here? The data is just so rich.
And there's something really special about the infrared. Infrared can actually see deeper into these star-forming regions.
Absolutely. That's one of the great things about infrared, is it really does reveal what's going on here in a really cosmic sense. And in general, what's happening in sort of this overall landscape is we have these gigantic, hot, young stars up here to the top of this rim, and the radiation and stellar winds from those stars is sort of pushing down and running into all of this. This is gas and dust, and of course we know that gas and dust is great raw material for newborn stars and baby planets. But there's a flip side to this story, and also a little bit of a mystery, because these same processes can serve to sort of erode away this material and stop star formation. So we have this sort of delicate balance going on of new stars being formed, but at the same time, the star formation is being halted. And for me, when I see an image like this, I can't help but think about scale. You know, every dot of light we see here is an individual star, not unlike our sun, and many of these likely also have planets. And it just reminds me that, you know, our sun and our planets, and ultimately us, were formed out of the same kind of stuff that we see here. We humans really are connected to the universe. We're made of the same stuff in this beautiful landscape.
And actually, the Carina Nebula was one of my favorite images from Hubble. So Hubble looked at this as well, right?
Absolutely, yeah. The Hubble image of this is also spectacular. We saw it in a different kind of light when Hubble took an image of this particular nebula. And then you can see amazing things with Hubble, but when we zoom in to this new image, we're able to see so much more detail. And of course, all of us, you know, I grew up on Hubble, and all of us love Hubble. And I'm so excited to see what these two amazing observatories are able to do really in tandem with each other.
Thank you so much. And again, congratulations. It's been a pleasure to be working on this with you. I'm just amazed by what's been going on.
I am too. Thank you.
So as we're wrapping up, one of the things that I really have to say is the journey that we've been going on is so very dramatic for me. So we've gone all the way from the birth of stars, and we have all the way from the distant galaxies to the birth of stars. This is where we all began. This was the whole point of the James Webb Space Telescope, to figure out our origins from the very, very early days of the universe to star and planet formation very nearby. So right now, I'm very honored to have our last special guest. This is the administrator of NASA, Bill Nelson. An honor to be with you, sir.
Hey, what a pleasure. What a banner day. It's clear that Webb represents the best of NASA. It maintains our ability to propel us forward for science, for risk-taking, for inspiration. And we don't want to ever stop exploring the heavens, nor stop daring to take another step forward for humanity. In the words of the famous Carl Sagan, somewhere something incredible is waiting to be known. I think those words are becoming reality.
Absolutely.
Thanks, Michelle.
An honor to have you here. Thank you very much. Wow. So this is a celebration for all humanity. If you've ever looked up at the night sky and wonder, whoever you are, wherever you are, this is your telescope. And we also salute the thousands of people who have dedicated part of their lives to making Webb a reality. I also want to give a big shout out for the superb media team who's helped bring Webb's story to the world. This broadcast is a joint effort of the superstar producers, animators, and social media specialists at the Canadian Space Agency, ISSI, NASA, and especially the Goddard Space Flight Center. Webb captures light in distant colors that the eye can't see, and you've actually made this visible to the world. So finally, if you go to nasa.gov/Webb-First-Images, you can download all of the images and data we've just shown in full resolution, and check back often. From now on, we share new discoveries from exciting new destinations around the universe. July 12th, 2022 marks a huge day for science, and it's only just the beginning. For everyone at CSA, ISSA, and NASA, I'm so very pleased you could join us. I'm Michelle Thaler. Go Webb.
astronomers are extremely lucky to benefit from absolutely superb facilities. And when you think of the deployment of Webb, I read this morning in the New York Times, there were 344 single point failure. Any of these 344 steps would have been able to break the whole telescope and to put it in hold mode for maybe a few weeks or a few months. So it is absolutely superb to see the technological success which is offered by our society as astronomers. And we have now the proof. We are living the dawn of a new era for the knowledge of planets, the knowledge of stars forming or dying, the formation and evolution of galaxies and cosmology. And this is really going to be significant, probably, I bet on the future, but it is going to be probably even more stunning than the successes, and they were important, the success of Hubble, the Hubble Space Telescope. We are lucky also, we astronomers, because we are living a golden age. Within the last 10 years, astrophysics and cosmology were awarded quite a large fraction of the Nobel Prizes in comparison with the size of our community. We had in 2020 a Nobel Prize for black holes, in 19 about cosmology and also about planets, Mayer and Kellogg. In 70, gravitational waves were awarded the Nobel Prize. In 2011, it was the acceleration of the universe, and even a bit earlier, and it was amazing to see John Mather, it was the CMB, the cosmic microwave background, which received the Nobel Prize. So we are really living in an incredibly rich period of discoveries and studies for our field. And I bet that the series of Nobel Prizes may not be finished for we astronomers. And I would like to conclude in saying that in this weird time, it is essential to see these international collaborations. And I was sad in a way to see, and we understand why, but some other countries were not mentioned at all during these few minutes of broadcast, while probably before February 24th, other countries may have been mentioned. And it is essential for us, I think, to maintain this international collaboration, because it is also the best way to try in our humble way to maintain peace on Earth. Thank you.
These beautiful results. I have a question to them. We had Hubble. We have this one now. So what is next? What can we do better?
The LUVEX will be a 12-meter in space. People are already working. Europe will be involved, and I think we have to make it happen. So it relies on all of you sort of to inform your agencies and push. That will be the next thing if you want to search for life.
The wide-angle infrared?
No, it's going to be an UV optical infrared.